infinite, because you have now infinite number of states in a finite energy, so you have a continuous distribution with no gaps in between. Now you are ready to understand what is happening in molecular solid, once you have seen this. Now let us start. Molecular solid, what am I going to do? Molecular solid means that these two hydrogen atoms are together to form a molecule, but these two are farther apart. Okay? So I'm going to bring them closer. I'm going to bring them closer like that. So hydrogen molecules, and I have condensed them. In order to have the molecular identity, these two must be closer together than that. And this is the case where you have more than one T. One T is defining this, and you have another T prime hopping strength, which is this. Obviously, T prime is much smaller than T. What's going to be the consequence? The consequence of it, first ignore T prime completely, set it to 0. Then you know the solution exactly. The solution is what? This T is going to give me one level here, one level there. Bonding, anti-bonding. And then again I'll get one bonding, one anti-bonding, one bonding, one anti-bonding. And this one will not talk to that because T prime is 0. Now switch on T prime. Primarily, this and this will interact, that and that will interact. And they have the same T prime. So now you have another infinite lattice that I have talked about, which are connected by T primes. So that these ones now will broaden, and this one will also broaden, but this broadening is going to be smaller than this separation. Simply because T prime is much smaller than the T. The T that pushes it down is larger than this T prime that can spread it out.
So like first order perturbation theory, very simply.
Absolutely, and that's why I started with saying T prime you set equal to 0, it's a small one, solve a molecular problem, and then you broaden it out. Now what have you done? You've got one set of bands here, one set of bands here, so the corresponding density of states will look like this. This is corresponding to the band of the bonding orbitals, this is a band of the anti-bonding orbitals. And there are no states in between. And now you fill in the electrons, you will fill in this one completely, and this one will be empty because they have exactly equal number. The bonding is always, because remember bonding had 2 electrons, anti-bonding had none, which means the bonding band will be completely filled, anti-bonding will be completely empty. Now you get an insulator with that band gap. This band gap is then controlled by, in some sense, this width is controlled by T, is a function of T. That was the original bonding anti-bonding splitting, and this bandwidth, as well as this bandwidth, is a function, small function of T prime, so that this gap is given by that function of T minus twice the function of T prime, because this is the function of T, you subtract this much and you subtract that much, that's the gap that remains. So you can see that since T has much larger than T prime, the finite gap opens up for the molecular solid. Okay? This is all just by hopping. This electron localization by electron-electron interaction I have not talked about, except for when I change the periodic table for you. This is all completely one electron theory to tell you what metal and insulator. This is basically something that I've written here. I hope you understand now. This, if the, take the example just to make sure that you understand this cryptic statement here. It says that if it did not hop, the energy will be orbital energy. What do I mean by that? That consider all these hydrogen atoms, infinite of them. All of them, the 1s orbital is occupied with one electron. And let us imagine that electron energy I write down as Es. So every side Es energy is there. And imagine that the T that couples them or hopping is equal to 0. It's a very artificial construction. And then ask the question, is it a metal or an insulator? It's actually a metal. If only the electron could hop from here to there, you see that one electron will take away from ES energy and put it at ES energy. So the energy doesn't change. So it doesn't cost you any energy to make the electron go from one side to the other. If I don't think of its spin, then this electron can go from here to there, and so the electron can go anywhere. Though the hopping strength is equal to 0, it appears that the electron can move, and the total energy of this system is going to be n particles multiplied by epsilon s simply. Because every electron has that energy. And whether that electron is sitting here, or two electrons sitting here, no electron sitting there, it's the same energy everywhere. So this is going to be the energy, and hopping is not going to cost me any energy in an artificial construct. So that's what is written here, that the total energy will be nothing but the orbital energy. We call this epsilon s is the orbital energy associated with the electron in that orbit. But the hopping, what I showed you, remember, this bandwidth that forms, so the orbital energy was at the center. This was the orbital energy. This, that minus zt stabilization comes because of hopping. T going to 0, this bandwidth goes to 0. So the system gets stabilized hugely because of hopping. And that is what is written down here. I just wanted to make sure that you understand these points. Okay. Now let us consider another situation. This part we have understood. Now we bring in the Coulomb interaction. I have said so far everything that I am talking about has nothing to do with Coulomb interaction. What would happen if there is Coulomb interaction? Well, this I said just now, the situation here, which is a metal within quotation, within a quote mark, because it's not going to hop, so T equal to 0, but it at least costs no energy if I can transfer the electron from one to the other side. But now imagine that electrons repel each other. Which electrons do? You know that. That is the Coulomb interaction. Now when this electron was sitting over here, and one was here, one was here, one here, every side had one electron. But then I said, no, take out this electron and bring it here. And I said that, well, that went to 0, but this is going to. That's not true, because these electrons are going to repel each other. And that's going to cost me some energy. So it's not going to be, whereas earlier everything was epsilon s, and that gave me n into epsilon s. Now what I have, this is 0, these are all epsilon s. This is twice epsilon s, but plus an energy which is equivalent to the energy with which the two electrons are repelling each other. Which means immediately you can see now the total energy of this limit is going to be n into epsilon s plus u. Which means with respect to this state where the electron did not hop, as soon as it hops, it requires energy. Without giving this energy, it will not hop, which means that there is no zero energy hop possible. Shazin? This is the Coulomb interaction strength. This U is the Coulomb interaction strength of two electrons on the same side. So that's the additional energy that's coming in, which means that as soon as I take into account the fact that electrons repel each other, I couldn't make it metallic the way I had talked about. Because now the hopping of putting two electrons at the same time costs me energy. So I'm going to generalize this concept and not stay with just one electron. This caveat you forget about, it is long range.
But this all still ignores spin, because when you bring in spin,
Absolutely, absolutely. I'm so far spinless fermions. So, one complication at a time. I mean, I shout at my students when they try to optimize or error minimization routine, changing more than one parameter at a time. Then you go crazy in multi-parameter space.
So DD, is that U not equal to 0 that will give insulator, or
U not equal to 0 will give you insulator. If U is equal to 0, you see the energy difference.
it's all 0 Kelvin argument then. I'm not taking into
temperature is not at all here. Nowhere I am bringing temperature. So it's all equal to 0 discussion.
I think temperature will not appear in our lecture series.
Pardon?
In our whole lecture series, temperature.
Temperature will not appear. Absolutely. And so, in fact, here you can see why that U equal to 0 will make it a matter. Right? If U went to 0, these two states have exactly the same energy, which are different by the fact that I have shifted one electron. That means shifting of electron costs you no energy. But as soon as it even smallest of a number, 10 to the power minus 23 electron volt, this is higher than that, and that's an insulator with the gap exactly equal to U. The gap is the energy that you need to give to a system to conduct, and that is equal to U in this model. That was the model where T was equal to 0 and U was not equal to 0. See, I am systematically building. First we looked at T equal to 0, U equal to 0. Which is the method. T equal to 0, U not equal to 0 is an insulator. Now I want T also not to be 0. Where T is finite, U is finite. Now what is the consequence of T being finite? I know that T finite gives me a W, the width. 2ZT, remember? Here there was no width. So what will be the consequence? It will be very similar, but then something similar to what I have done here, and let's go to that. And let me generalize the situation that now I don't have one electron at each side, but n electrons at each side. The argument is so general, it remains identical. Let us look at it. So here is a, instead of a one-dimensional array, I have given you a square arrangement of atoms. Each side has n electrons. These are d orbitals because I am talking about transition metal. N electrons at each side. In order to do charge transfer, I have overshot the 1 hour. Okay. So I should stop somewhere. Okay.
There is a continue after Tn. So it's after you.
That's fortunately behind me.
When you want to.
There is a T between to the left.
Okay. When do you want the tea break? After a little more? Because I'll finish this part and then.
Once I learned in a conference in North India, so when somebody said ducks are something.
I'll ask exactly the same question that I asked here. How much energy does it cost to take one electron from here and put it there? Everywhere it was n electron, but the one side that I take the electron out, it becomes n minus 1 electron. And the side where I put it down, it becomes n plus 1 electron. That's all I have done, and I'm asking what is the consequence. If there is no Coulomb interaction, initially I had n electron at each of the m site, and each of the site had an energy epsilon. So the total energy was m into epsilon. M sites, these atomic sites, there are m of them. Each site had n electron before the hopping. So total number of electrons were m into n, and each of those electrons had an energy of epsilon. So the total energy I corresponds to initial. So the total energy was n into epsilon. After the hopping, I have removed these two sides. One side that has less electron, one side that has more electron. So I have n minus 2 sides which have still n electron, correct? And they have epsilon energy. I have one side with n minus 1 electron, which is epsilon energy, and I have one side with n plus 1 electron, which is epsilon energy. Of course, if you add together, you get Mn. Right? So that means this is a metal because you see that the initial state and final state where I have moved an electron has not costed me any energy. That F corresponds to final state after the movement. So that's a metal. You see that the energy of excitation of one electron from one side to the other to any other arbitrary site is exactly equal to 0. And that's a strict definition of a metal. So it's a metal clearly. And that's what we have got. For one electron we have done per side, you can see that exactly the same picture emerges if you have n electron per side. Okay. Now, bring in the Coulomb interaction. In this energy calculation, I did not take U, Coulomb interaction. Now I must bring in that. So when I do that, so again these are those m sites with n electron at each side. I take one electron from here and put it there. This becomes n minus 1, that becomes n plus 1. Initial state, how much was the total energy? At n sites, each of the sites with n electrons, so m into n into epsilon was the occupancy energy of n electrons. But each of these n electrons was interacting with each other. Pair-wise, that's how many pairs are possible? N situ. Correct? So there were n situ pair-wise interaction, each pair costing U energy, and there are m such sites. So each of the n site has n situ into U additional energy, which I've added in, multiplied by n, because that happens at all the sites. This is before the hopping. Have you answered? This is okay? Now take the electron out, and we will follow through exactly the same. Two sides take out, it's the same part, n into epsilon, n situ U, just like here. Here, one side has n minus 1 electron with energy epsilon, and n minus 1 electron interacting pairwise is this much Coulomb energy. And another side, this one has n plus 1 electron with epsilon, orbital energy, and n plus 1 pairwise interaction with U. Work this out and what the difference of the energy is exactly what we had seen over here. That tells me that if I have this U very large, of course if U is not there, hopping gives me a bandwidth, which is the W. But U makes my hopping require energy. So if I have a very large U, much larger than the bandwidth, I'll find one piece here which is completely occupied, and this kind of hopping would be prohibited by U, which is this energy, and the empty state should lie there. Because I cannot hop to the other side, because Coulomb interaction energy is larger than the energy I gain because of hopping. The energy that I gain by hopping is W, the bandwidth. And the energy that I lose is U. So the hopping costs me so much more energy. And you can see that the gap between the two is U energy that I require for hopping, that you have already understood here, minus W by 2 minus W by 2, which is U minus W. Which tells you exactly that the hopping gives me bandwidth which stabilizes, so minus W, gap becomes less, but U adds to the gap. So the band gap becomes U minus W, so the band gap increases as I increase U and decreases as I increase hopping, which is W. So if U becomes equal to W, then you can see that this one will touch each other, because this is W by 2, this is W by 2, and that's U. So that's a critical U value. If the U value becomes smaller than W, these two will overlap. This was unoccupied, this is occupied, so the system becomes metallic. And if U is larger than W, then I have a gap, because it's U minus W is positive, that means there's a gap in between. That means the system is